You think black holes suck things in like cosmic vacuums. Everyone thinks that. Every documentary, every article, every science teacher. Black holes suck. Nothing can escape their pull. They vacuum up everything around them. Not approximately wrong. Wrong. Black holes don't suck any more than the Earth sucks. And you're standing on Earth right now, not getting sucked into its center, so clearly something's off about this metaphor. Here's the problem. You've been given a word, suck, that smuggles in a completely wrong mechanism. Suction requires pressure difference. Your vacuum cleaner works because the motor creates low pressure inside and atmospheric pressure outside pushes air in. Space has no atmosphere. There's no pressure to push with. The mechanism you're imagining, the thing you picture when someone says black hole sucks, doesn't exist. So what's actually happening? Simple question. Why do things fall into black holes? You can't answer that. Not really. You'll say gravity, like that explains something. It doesn't. That's just renaming the mystery. Why does gravity make things fall? What's the mechanism? What's physically happening between the black hole and the object that's falling? Think about what you're claiming. A black hole sitting there doing nothing somehow reaches out across empty space and pulls things toward it. How? What reaches across that space? What carries the force? Your intuition probably imagines invisible ropes or some kind of pull. That's not an explanation. That's a cartoon. The truth is stranger and more beautiful than any cartoon. And it's going to completely change how you think about gravity itself. Let me show you something right now. Take your phone, the thing you're probably holding, and drop it. Just a few inches. Catch it before it hits anything. What did you just observe? Your phone fell, accelerated downward. You've seen this 10,000 times. It's so familiar you think you understand it. You don't. Why did your phone fall? Gravity, you say. Fine. What's gravity doing? Pulling. You answer. Wrong. Stop. There is no pull. That word carries mechanical assumptions that don't apply. The Earth isn't grabbing your phone. There are no invisible ropes. No mystical force field reaching up and yanking things down. Here's what's actually happening. Your phone is moving through space-time. Space-time is curved around massive objects. The phone follows the straightest possible path through that curved space-time. From the phone's perspective, it's not accelerating at all. It's in free fall, following a geodesic. You and the Earth are accelerating upward into the phone. That's why you feel weight. The ground is pushing up on you, accelerating you away from the geodesic path you'd naturally follow. Wait, you're thinking, the ground is accelerating upward, but I'm not moving. Yes, you are. You're accelerating right now. You feel that acceleration is weight. The chair pushing up on you, that's an applied force, making you accelerate away from free fall. If the chair disappeared, you'd stop accelerating and start following a geodesic. That's what falling is, stopping acceleration and following the natural path through curved space-time. This is going to take some building, but by the end, you'll see why black holes don't suck, what they actually do, and why that's so much more interesting than any vacuum metaphor. The story starts with Newton, 1687. He's trying to explain why planets orbit the sun and why apples fall from trees. Same phenomenon. He realizes gravity, but he's got a problem. Newton knows gravity follows an inverse square law. Double the distance, quarter the force. Triple the distance, 1/9 the force. He can calculate orbits perfectly with this. The numbers work, but he has no mechanism. He writes that one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Newton knew his own theory was incomplete. He could describe what gravity does. He couldn't explain how it works. That how took another 228 years. Enter Einstein, 1915. He's been thinking about a weird fact. Gravitational mass and inertial mass are exactly equal. The mass that determines how hard gravity pulls on you is identical to the mass that determines how hard it is to accelerate you. Why? That's suspicious. Different properties, same number. Always? Here's Einstein's insight. They're the same because there's no gravitational force at all. Gravity isn't the force pulling you. Gravity is the curvature of space-time itself. Mass curves space-time. Objects follow the straightest paths through that curved space-time. Those paths look curved from the outside, so we invented a word, gravity, to describe the apparent force. But there is no force. There's geometry. Think about that for a second. Everything you feel as the Earth pulling you down is actually space-time geometry. The Earth's mass curves space-time around it. You're trying to follow a geodesic, a straight line through curved space-time. The ground gets in your way. The ground accelerates you away from that geodesic. That acceleration is what you feel as weight. Now here's where it gets interesting. The curvature of space-time isn't some abstract mathematical trick. It's measurable, physical, real. Take two clocks, identical atomic clocks, synchronized perfectly, put one on the ground, put one on a mountaintop, wait, come back. The mountaintop clock is ahead, not by much nanoseconds per day, but ahead, consistently, measurably. Why? Because time runs at different rates in curved space-time. The clock on the ground is deeper in Earth's gravitational well, deeper in the curved space-time. Time runs slower there, not because the clock is broken, because time itself runs slower in more strongly curved space-time. We measured this, we've measured it thousands of times. GPS satellites orbit at 20,000 kilometers altitude. They experience weaker gravitational time dilation than receivers on the ground. If we didn't correct for this, if we pretended space-time wasn't curved, GPS errors would accumulate at 38 microseconds per day. That's 11 kilometers of positioning error per day. Your GPS works because we account for curved space-time. If space-time weren't curved, GPS would fail. This isn't theoretical, this is engineering. We build the curvature of space-time into our technology because that's how reality works. Now, black holes. A black hole is what happens when you curve space-time so severely that geodesics, those straight paths through space-time, literally can't point outward anymore. Beyond a certain boundary called the event horizon, every geodesic points inward. Every possible future path through space-time ends at the singularity. This is radically different from suction. Suction redirects existing paths by applying force. Black holes don't redirect anything. They don't apply force. They curve space-time so severely that the paths themselves all point inward. Here's the math. The Schwarzschild radius, the radius of the event horizon for a non-rotating black hole, is r_s equals sine 2gm psi quatre, where g is Newton's gravitational constant, m is the mass, and c is the speed of light. For the sun, 3 kilometers. Compress the sun to a sphere 3 kilometers in radius, and it becomes a black hole. Not because it suddenly starts sucking harder. Its mass hasn't changed. Its gravitational field at any given distance hasn't changed. But now the curvature is so extreme that inside 3 kilometers, space-time itself is bent beyond the point of return. For Earth, 9 millimeters. Pack Earth's entire mass into a sphere 9 millimeters across, you get a black hole. Again, same mass, same gravitational field at any distance. But the geometry is broken in a new way. The sun right now exerts the same gravitational influence on Earth as a 3-kilometer black hole with the sun's mass would. Exactly the same. If the sun suddenly became a black hole, hypothetically, this can't actually happen to a star. The sun's mass, Earth, would keep orbiting. Same orbit, same period. Nothing would change gravitationally. Because black holes don't suck. They curve space-time. And the amount of curvature at any distance depends only on the enclosed mass, not on whether that mass is a star or a black hole. Let me show you where intuition goes completely wrong. You're probably imagining the event horizon as some kind of boundary you cross, like going through a door. On this side, you're fine. On that side, you're doomed. Wrong framework. The event horizon isn't a physical barrier. Nothing happens when you cross it. No force, no wall, no sudden change. You wouldn't even notice. An observer falling into a stellar mass black hole would cross the event horizon without feeling anything special at that moment. What's actually happening? The causal structure of space-time has changed. Before crossing the event horizon, outward exists as a direction you can point in space-time. After crossing, outward is no longer a direction in space-time, it's a direction in time. Specifically, it's the past. Moving outward from inside the event horizon is as impossible as moving backward in time. Not because something's preventing you, because the geometry doesn't permit it. There's no direction through space-time that leads out. All directions through space-time, every possible trajectory, every geodesic lead to the singularity. And you follow geodesics. That's what matter does. Think about what this means. You can fire your rockets. You can accelerate as hard as you want, doesn't matter. Acceleration is deviation from a geodesic. You can deviate from any particular geodesic. But all geodesics inside the event horizon end at the singularity. You're not fighting a force, you're fighting the structure of space-time itself. The future, all possible futures, contains the singularity. The singularity is in your future the way tomorrow is in your future. Not spatially ahead, temporally ahead. Now let's talk about what we actually observe. Because we've seen black holes. Not directly, you can't see something that doesn't emit light. But we've seen their effects, measured them, mapped them. Take Cygnus X1, discovered 1964. It's a binary system, a blue supergiant star orbiting something invisible. We measured the orbital period, 5.6 days. We measured the orbital velocity from Doppler shifts. From Kepler's laws, we calculated the mass of the invisible object, 15 solar masses. What invisible and 15 solar masses? Not a planet, not a star. We'd see it. Not a white dwarf. Maximum mass for white dwarfs is 1.4 solar masses. Not a neutron star. Maximum mass around 3 solar masses. It's a black hole. First confirmed stellar mass black hole. We've now cataloged dozens of stellar mass black holes this way. Invisible objects in binary systems, masses determined from orbital mechanics, too massive to be anything but black holes. But the real breakthrough came in 2019. The Event Horizon Telescope. Not a single telescope, an array of radio telescopes across Earth, linked to form an effective aperture the size of the planet. Target, M87*, the supermassive black hole at the center of galaxy M87. What did we see? A ring of light, photons from infalling matter, heated to billions of degrees, orbiting the black hole at the photon sphere, the radius where light itself can orbit. Inside, shadow. Not because there's no light there, there is, but because any light emitted inside a certain radius curves around and falls in. The shadow is larger than the event horizon itself because light bends around the black hole. The diameter of that shadow, 42 billion kilometers. The mass, 6.5 billion solar masses. The image matched predictions from general relativity exactly. The shape, the size, the brightness distribution, everything matched. We photographed curved space-time, we saw the geometry, and in 2022 we did it again. Sagittarius A Slaw, the supermassive black hole at the center of our own galaxy. Mass 4 million solar masses, distance 26,000 light years. Same technique, same ring structure, same conformation of curved space-time geometry. But here's where it gets truly weird. Let's talk about what happens if you actually fall in. First, from your perspective, falling in takes finite time. You cross the event horizon. You continue falling. You eventually hit the singularity. The trip has a duration. It ends. For a stellar mass black hole, the trip from event horizon to singularity takes microseconds. For a supermassive black hole like M87*, it takes hours. But from an outside observer's perspective, you never cross the event horizon. Never. They see you approach the horizon. They see your clock slow down. They see the light from you redshift, not just gravitational redshift, but time dilation redshift. You appear to freeze at the horizon, light redshifting toward infinite wavelength, fading away. You never cross from their perspective. Not because you stop, because the coordinate system breaks. The time coordinate becomes infinite at the horizon. This isn't paradoxical. Both perspectives are correct. You cross in finite proper time. You never cross in coordinate time. That's relativity. Different reference frames, different descriptions, same physics. Second, tidal forces. These are what actually kill you. Not the black hole sucking you in. Not the event horizon. Tidal forces. Here's the mechanism. Gravity follows an inverse square law. Your feet, closer to the black hole, experience stronger gravity than your head. That difference, the gradient in the gravitational field, stretches you. This is true near Earth, too. Your feet are pulled slightly harder than your head right now. But the difference is tiny. You don't notice. Near a black hole, the gradient is enormous. For a stellar mass black hole, the tidal forces become deadly long before you reach the event horizon. The difference in gravity between your head and feet would rip you apart, a process cheerfully called spaghettification. And this is beautiful, tidal forces depend on the gradient, not the absolute strength. For a supermassive black hole, the event horizon is enormous. The curvature at the horizon is more gradual. You could cross the event horizon of M87* and survive. The tidal forces at the horizon would be less than what you feel on Earth. You'd be inside, doomed, unable to escape, but physically intact for hours, until you get closer to the singularity. Then the tides kill you, but not because of suction, because of the gradient, because of the curvature of space-time changing over distance. Third, the singularity itself. This is where our physics breaks. General relativity predicts a singularity, a point of infinite curvature, infinite density. But we don't believe that. Not really. Infinities in physics usually mean your theory has exceeded its domain of validity. General relativity is a classical theory. It ignores quantum mechanics. At small enough scales, quantum effects dominate. We need quantum gravity. We don't have it yet. What happens at the singularity? We don't know. The honest answer, we don't know. We have theories, string theory, loop quantum gravity, others. We have speculation. We don't have evidence. We don't have a tested theory. The singularity is where understanding ends. But here's what we do know. Black holes exist. We've mapped them. We've photographed them. We've measured their masses, their spins, their effects on surrounding matter. We've confirmed that they curve space-time exactly as general relativity predicts. We've used them to test relativity in the strongest gravitational fields we can observe. And they don't suck. They never suck. That metaphor is poison. It makes you imagine a mechanism, pressure difference, suction, pulling, that doesn't exist. Here's what they do. They curve space-time, mass curve space-time. Black holes are extreme curvature, so extreme that geodesics, the natural paths through space-time, all point inward beyond the event horizon. Matter follows geodesics. That's not a force, that's geometry. Right now, you're sitting in curved space-time. The Earth beneath you curves space-time. You're trying to follow a geodesic free fall. The ground accelerates you away from that geodesic. You feel that acceleration as weight. The mechanism underneath your everyday experience of gravity is the curvature of space-time. Black holes are the same phenomenon, cranked to 11. Same mechanism, different magnitude, nothing new required. Just Einstein's equations taken to their logical extreme. So when someone says black holes suck, you can correct them now. Black holes don't suck. They curve space-time so severely that all paths lead inward. Matter follows those paths not because it's pulled or sucked, but because that's what matter does in curved space-time. It follows geodesics. The universe doesn't care about your intuition. Your intuition evolved for throwing rocks and avoiding predators on the African savanna. It did not evolve for understanding relativistic space-time geometry. That's why learning physics feels strange. You're building new intuitions, intuitions that match reality instead of evolutionary convenience. And reality is stranger than any vacuum cleaner metaphor. Black holes aren't cosmic drains. They're regions where space-time curvature has become so extreme that the causal structure breaks, where the future is the singularity, not as a destination, but as an inevitable moment in time, where light itself cannot escape, not because something's pulling it back, but because outward has ceased to be a direction in space-time.